So this is lecture number the previous one was 13, if I'm not mistaken. Special case, lecture 12. This is 13. So lecture number 13. And today is the 24th. And we'll be talking about exponential functions. All right. So how do we begin this story of exponential functions? Quite simply, so exponential functions are of this form. So what's the function notation? So usually we give, or the introduction to any kind of function by its function notation. So whenever you see a function that has this form, you should know that we're speaking of exponential functions. So this is a typical exponential function. Now I want to highlight certain things from this function notation. A and B, they're constants, okay? They're real constants. So this is a real constant. I should just write real constants. Yeah, real constants. One thing is that the b value is normally it normally cannot equal 0. It doesn't make sense for you have to have an exponential function that you raise that this base is a 0. And also a does not equal 0. So I should write that for both. If you have a equal to 0, then you really don't have any function. You just have the constant function. So normally these are non-zero real constants. And one thing to note is that what makes this exponential is that your variable, so note, your variable, in this case x, is an exponent. Normally, what do we have in polynomials, in rational functions? We have our variables as a base. But in this case, our base, b is my base. So this is the base. So normally my base now is my constant, and my variable is my exponent. So here we can have like little example. What's the difference between something like x squared versus something that has this form? 2 to the x. You see the difference? They both have x's in them, and they both have 2's in them, but they're completely two different functions, right? On the left, you have what's called a power function, right? Your base is x, your exponent is 2. On the right side, you have what's called an exponential function. It's exponential. Your base here is 2, and your exponent is x. See that? So now we're going to be dealing with these kind of functions where the base is a number and the exponent is a variable. Okay. Now, what kind of categories do exponential functions fall into? There's two categories. So we have two categories of exponential functions. So one of them is a growth. So I should say exponential growth. So this is when your function grows. And when does that happen? That happens when my base, so exponential growth, occurs when your base, b, is bigger than 1. And to call this, we name this b value, that the one that we have right here underneath the exponent. This is called a growth factor. We have a growth factor. Now, what would that look like if we were to give a little sketch? So exponential functions have this little graph here. So when you have a growing function, exponential, to the right, it just blows up. And to the left, it gets really, really close to 0. This is an example, of course, just an example of a function. I'm gonna call it b to the x, okay? The a value here is just 1, the a equals 1. So if the a value equals 1, I start at 1 here. The y-intercept is 1. Now, what would be my domain? And what would be my range? Well, my domain is all real numbers, negative infinity to infinity. And my range is 0 to infinity. Exponential functions have horizontal asymptotes, but they don't have vertical asymptotes. So this does have a horizontal asymptote. And the horizontal asymptote is the x-axis, which is the same thing as saying y equals 0. Okay, so this is a typical exponential growth function, and it goes like this. The domain is all real numbers, the range is everything above the x-axis, and the horizontal asymptote is y equals 0. And how do I know that's the case? We know this because as the x values approach negative infinity, my y values approach 0. So as I get closer and closer to the left, right? As I move along to the left, as long as I want, this y values here get really, really tiny, and they become closer and closer to 0, but never actually cross 0. So that's the exponential growth version of the exponential function. And there's another one. We also have exponential decay. And exponential decay occurs when my factor is no longer called a growth factor, it's called a decay factor. And that's when my b value is something in between 0 and 1. So when that happens, this b value becomes a decay factor. So when my b value is bigger than 1, I got growth. When my b value is between 0 and 1, I have a decay factor. And what does that result in? If I have the graph. And this time I am also going to use this notation here, b to the x. The only difference, does anybody know what this would look like? The growth, the decay factor, the decay function. B is greater than 1, so it cannot be 1. Actually, it can be 1. In terms of the function can equal 1. So the decay is going to look exactly like the growth. It's just going to be flipped. It's going to be reflected. It's going to be something that looks like this. That's going to be decay. So it's going to have all of the characteristics as the previous one, with the domain being all real numbers, the range being everything from 0 to infinity, and the horizontal asymptote also being y equal to 0. The only difference is the following. As x approaches positive infinity, y approaches 0. I should say this is part A. Part B, as x approaches negative infinity, y approaches infinity. So when we describe end behavior for this function, it's flipped. It's the opposite of what growth is. Growth here, as x goes to negative infinity, so as you move to the left, the y's go to 0. So I should write this as part A here of end behavior. Part B says that as x goes to positive infinity, y goes to positive infinity. So as you move to the left, you get to 0. As you move to the right, it goes up. That's growth. Decay, though, is different. As you move to the left, this grows. But as you move to the right, it decays. And we normally read from left to right. So normally, we call this a decay, and we call this a growth. So these are the major categories or groups of exponential function. So you have exponential function, it could either be a growth or a decay function. Okay? All right. So now let's talk about some specific ones in general. And in this case, I want to talk about evaluating an exponential function. So suppose I have the function, let's just start with 2 to the x. And I want to evaluate f of 5. How do I evaluate this function? Well, if my x value is 5, right, I'm going to plug in wherever I see x to be a 5. And 2 to the 5th power equals 32. It's always useful to know the powers of 2's. Does everybody know the powers of 2's? You got what? 2 to the 1st is 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. 2 to the 5th is 32. 2 to the 6th is 64. 2 to the 7th is 128. 2 to the 8th is 256. 2 to the 9th is 512. 2 to the 10th is 1024, and so on and so forth, right? You get you double, double, double. But it's good to know these powers of twos. And can anyone tell me where they have seen these numbers before in their daily lives? Has anyone seen these numbers before? In some realm, in some area of their lives? Space sizes. What do you mean by space sizes, Gabriel? Right, that's right. It's memory. Yes, a lot of our memory devices that require memory, uh, like any laptop, phone of any sort, right? They're always have a certain memory attached to it, memory size. And it's one of these numbers. It's either to say 64 gigs or 128 gigs, right? Now everything almost is up in this category now. It used to be in this category, when they first came out, when the iPhone came out, like 8 gigs seemed like a lot back 15 years ago. Or yeah, or 13 years ago. But now everything is getting bigger and bigger. Now you have laptops that can, have 1 terabyte of storage. So yeah, so these numbers here appear a lot in technology. And it's interesting to see why that's even the case. Like, why do we care about the powers of twos? And why do they present it that way? Why don't they have powers of threes or some other kind of number? That's something to think about. Okay. What if I have something like this? F to the negative 2/3. Same idea, right? You just plug in. That's all we're doing. Plug in. And then you can write this as 1/2 to the 2/3. And you can leave it like that. Put it in your calculator, find a number. But I like just leaving it as a radical here. So this would be the cube root of 4, because this is the 3 in the denominator indicates the root, and the 2 represents the squaring. So it's going to be the cube root of 2 squared, which is 4. And you put that in your calculator and you get a number. But this is okay. Just leave it as in this form. F of, let's say if I have something like crazy like pi. Now this will be interesting. You're taking you're taking 2 and you're raising it to the pi power. And if you want to know what that is, you can just put in your calculator. 2, we raise it to the pi, and I get 8.8249. So this is approximately 8.8249, and this goes on forever. Okay, so evaluating functions is not necessarily a big deal. Okay. Now, what I'm going to be interested in particularly is the graphs, right? So this is going to come up again, this kind of information here. So the graphs of exponential functions, that's going to be important. Okay, so what are the parent functions? Okay, that's the first thing. The parent functions, we've kind of discussed it, but without really saying that they're parent functions. So parent functions of exponential functions are of this form. F of x or y equals b to the x. That's it. And of course here b does not equal 0. So that's going to be my parent function. So 2 to the x, 5 to the x, 10 to the x. Those are parent functions. Okay, so just examples here. Y equals 2 to the x, y equals 5 to the x, y equals 10 to the x, dot, 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 so on and so forth, right? And all of them, all of these, just one thing, all of these, the y-intercept is always going to be, so if the a value is not here, we're assuming that the a value here is 1. This is the a value. So the y-intercept is always going to be 0, 1. For parent functions, my y-intercept is always 0, 1. And how do I know that? How do I find a y-intercept again? That's when x equals 0, isn't it? So if my function has b to the 0th power, I get anything to the 0th power is 1. So that's the reason why the y-intercept is always 0, 1. What else do we know about the parent functions? The domain is all real numbers. That's always going to be the case. The range is above the x-axis, and the horizontal asymptote is always going to be y equals 0, the x-axis, okay? So these are my parent functions. Now, of course, we're not just going to stay there, right? We're going to do certain things to it. And also, you can also consider these as parent functions. Like if you have 1/2 to the x, or if you have any fraction, 4/5 to the x, these are also going to be in that same category. Okay? And they have all of these characteristics. So let me write this as the characteristics. Okay, so we have the domain, the range, and the horizontal asymptote. Now, of course, we're not going to stay here. We're going to talk about the transformations. Transformations of exponential functions, right? So suppose I have a function like this. So the first thing I'm going to ask is, what is my parent function? So what is my parent function for this function here? Oh, one thing, yeah, and this here. Yes, my parent function is 2 to the x. Now, what are the transformations? What kind of transformations have I applied to the parent function? So there's two things here, right? There's that negative sign, and there's this 3 here. So these all indicate some kind of transformations. If I put a negative in front of the x, what does that do? It's a reflection. Very good, Sydney. And what kind of reflection is it? Reflected across the x or the y-axis? That's right. It's across the y. So the first thing is we reflect reflection across y-axis. That's what the negative does. And then what does the 3 do in front? It does a stretch. What kind of stretch is it? Is it a vertical stretch or a horizontal stretch? Very good. Very good. This is a vertical stretch. By a factor of 3. So that's what it is. Now, if I want to give a little sketch, what I'm first going to draw is the parent function. I'm going to draw it with a dotted line here. So my parent function is 2 to the x, so I know it looks something like this, right? This is my parent function, y equals 2 to the x. Now, what do I do to this parent function? I reflect it across the y-axis. So when I reflect it, I get this. You see? So my parent function represented exponential growth, and then when I reflect it, I got decay. And so this would be y equals 2 to the negative x, right? And then what do I do after this? So after I reflect across the y-axis, I stretch it by a factor of 3. So my original y-intercept was 1, and now when I stretch it by a factor of 3, I'm no longer at 1, I'm at 3. So then I'm going to have a stretch. So this is going to be my function g of x. And then what's going to be my domain? We talked about the domain already. Domain is all real numbers. So this is a typical exponential function that their domain is going to be all real numbers. The range, that might change depending upon how we transform it. But in this case, there's no vertical shift. So because we didn't shift it up or down, we just stretched it, the range still remains the same. And so does the horizontal asymptote. That remains the same. And if you want to talk about end behavior, right? If you want to talk about the end behavior of this function, then as x goes to infinity, y goes to negative infinity. And as x goes to negative infinity, y goes towards positive infinity. Okay, so that's our function g of x. 2 to the negative 1 power. So that 3 to the negative 1, that creates 3 times 2 to the negative x power creates a decaying function, and it's slightly stretched, slightly. Okay. All right. So now, let me give you another one of these. What if I get something like this? Oh, y equals 2 minus 1/3 to the x. So what is my parent function here? So what would you say my parent function is for this one? So remember the parent function, we want the we want the b value. So the b value here, it has to be positive. Here the b value here is 1/3. So we can say that the parent function is 1/3 to the x. Now remember, when my b value is between 1 and 0, what do I have? I have a growth or a decay. So we have a decay. So be mindful of that. So my parent function is a decay function. In this case, my parent function was a growth function. And again, we can use either one as a parent function. So my parent function is decay, and I should know all about parent functions. The domain is all real numbers. The range is above 0. The horizontal asymptote is y equals 0. and so on. Now, what are the transformations that I'm applying to this parent function? What, there's only two of them. So can anyone identify the two transformations that I apply? And if you want, you can rewrite this as negative 1/3 parentheses to the x power plus 2. I don't know if that might help a little bit. So Andrew, that's right. So there's a reflection across the x-axis, and that reflection is due to that negative that's in front, right? It's in front. So that one here is, let me see if I can move this over. So that negative is a reflection across x-axis, right? And then, so it's not a vertical stretch, it's a vertical shift upwards. So this is for the +2, this is a vertical shift up. So this is gonna be, a vertical shift by 2 units. By 2 units upward. Okay. So let's give this a sketch. So again, I'm gonna always base it off of my original parent function. So my parent function is a decaying function. And I know for a fact it's gonna cross 1. This is part of the characteristic of being a parent function of exponential functions, because if you raise it to the 0th power, anything to the 0th power is 1. So it'll always cross 1 as the y-intercept. So this is my parent function. And then what happens to this parent function? It's reflected across the x-axis. So then I'm going to have something like this. And this is -1 now. It crosses that -1 because of the reflection. So this is y equals -1/3 parentheses to the x. And then after I do that, what happens? I vertically shift upward by 2 units. So I move all of this by 2 units. And not only do I move the graph itself by 2 units, I have to move the horizontal asymptote by 2 units. So if my horizontal asymptote of my parent function was y equals 0, if I move it up by 2, now this is my new horizontal asymptote, y equals 2. And if my y-intercept was at -1, if I move 2 units up, now it's going to be at 1. So then I'm going to have something that looks like this. Do you see that? And this is my function. This is my function, y equals 2 minus 1/3 to the x. So again, I'm just following the orders of the transformations based upon the parent function. And now, let's talk about the characteristics of this function. Now this one here is quite different from the previous examples, right? The domain, like I said, exponential functions, it's all real numbers. So that's like the easiest part. Now, what's going to be the range for this function? What's going to be the range? Anybody? That's right. Thank you, Sydney. It's negative infinity to 2, and we exclude 2 because 2 is the, well, what is 2? 2 is excluded. And why is it excluded? What is it known as? So the horizontal asymptote would be what? Y equals 2, right? We just said that the horizontal asymptote has now been shifted upward. So now my horizontal asymptote is y equals 2. What's my y-intercept of this new function? So this is characteristics of y equals 2 minus 1/3 to the x. So the domain is all real numbers. The range is negative infinity to 2. The horizontal asymptote is y equals 2. The y-intercept, Andrew, is not 0, comma. Wait, actually it is. Sorry. I just saw it. I think I just erased this or something. Wait. So I think this might be bugging out here. I'm pretty sure this was over here, right? Yeah, it's 0, comma 1. You're right, Andrew. So it's 0, comma 1. And what else do we have? And the end behavior. How do we represent the end behavior? So the end behavior, as x goes to infinity, what does y approach? As x goes to infinity, y approaches what? Chen, so the reason why there's so many curves, and if you can tell, they have different, the dotted ones are the ones that we don't focus on. What we care about is the final one, right? What do we care about? We care about this final one, and that's why we get this green curve, right? But if I just give you the green curve, I would be remiss to show you how we get the green curve. And then we get the green curve based upon our original parent function, right? And we know that the parent function has this form. We know it because we just talked about it the whole time. And then after this, right, after I recognize the parent function, I'm literally just looking at, it's like a recipe. I'm just going through the instructions. So the recipe, first of all, tells me to do what? It tells me reflect across the x-axis. So I take this parent function, reflect. I get the blue one. So this is after I reflect, right? Reflect. And then it tells me, after you reflect, please move it up by 2 units. So I take the one that I just reflected and I move it up by 2 units. It is hard to do this and for you to just see the picture and be like, oh yeah, I understand. Um, uh, if technology permits someday, somehow, I'm pretty sure there's a way to do this where it's almost like a simulation and seamless. Okay. I don't understand how the y-intercept is 0, comma 1. Okay. This is well, it's 0, comma 1 because of this of what I just explained. Our parent function, right, is 0, the y-intercept is 0, comma 1. Every parent function for exponential functions, whether they be decay exponential functions or growth exponential growth functions, they all cross 0, comma 1. Why? Because when you plug in, I think I mentioned it up here, if you plug in 0 to any number, if you raise any number except for 0, if you raise any number but 0 to 0, you get 1. So there, henceforth, the y-intercept is 0, comma 1. But again, what am I doing to the parent function? It says reflect across the x-axis. So reflect, please. If I reflect, my y-intercept is now what? 0, comma negative 1. You see? Yeah, it's 0, comma -1 now, after I reflect across the x-axis, correct? I'm just reflecting what I see. So everything, all the y values are just reflected, are -1. And then after this portion, which is this after this command, it tells me to shift it up by 2 units. What is, if I shift up by 2 units, I'm moving all the y values up by 2 units. So if my y-intercept at this point was 0, comma -1, I move 2 units upward, and I get 1. And I move everything up by 2, everything up by 2. Even my horizontal asymptote is moved up by 2. So that's why my y-intercept is 0, comma 1 again. My horizontal asymptote is y equals 2. And my range is -infinity to 2, excluding 2. So yeah, everything is based upon the parent function, and from there you should be able to identify the transformations and apply the transformations to the graph so you get the final graph. And now we're at the end of this, no pun intended, end behavior. So as x approaches infinity, what does my y value approach? So be careful. This is look at the green function, right? Look at the green function. As my x values approach infinity, so it's like saying moving to the right. As my x values approach to the right, as much as I want, as far as I want, what do my y values approach? Not -infinity nor infinity. Remember, don't disregard this. This is a what? A horizontal asymptote. So then my y values are approaching the horizontal asymptote. So yes, so it should be 2. You see that? That's why it's the horizontal asymptote. I'm approaching it. But if I go in the reverse direction, as x approaches -infinity, then what does my y value approach? Well, I'm going in the opposite direction. My y value gets more and more negative. So we're approaching -infinity. Okay, any questions about these transformations? Do you see how we're doing this again? We're talking about parent functions. So last time we talked about parent functions for rational functions. And then we saw, oh, if you apply transformations, we get a new kind of function. Same thing with exponential functions. We got a parent function, and then we're going to apply transformations to it. Same thing is going to happen when we talk about logarithmic functions. We have a parent function, and then so on and so forth. This is the same kind of style that appears again and again in this course. Pardon me. Okay. Okay. So I'll give you one more of these kind. So I have a function that looks something like this. So again, what is the parent function? What are the transformations? So what is my parent function? So my parent function is simply a number raised to the x power. So what is that number? What is that base? It's 2, right? So it's going to be 2 to the x again. So that's my parent function, 2 to the x. Now, what are my transformations? And I only really have 2 of these. So what kind of transformations do I apply to this parent function? A vertical shift upwards, yes, that is one. And it comes from right here to +1 is a vertical shift. And what about this one here? What does this indicate? When you subtract 4 to the x only, what kind of shift is that? That's right. So 1 is the horizontal shift to the right. So this is number 1 here. And then 2, I have a vertical by 1 unit, sorry, by 4 units. And 2, I have a vertical shift upward by 2 units. Does everybody follow? So I'm shifting the 2 to the x, I'm shifting that parent function, I'm shifting it over to the right by 4, and I'm moving it up by 1. That's all I'm doing. Shift it right to the 4 and move it up by 2. I mean by 1, pardon me, why am I doing 2? By 1 unit. So shift the right by 4, up 1. Okay, so then I want to draw this out. Sketch it out. So again, the parent function, okay, I'm going to draw it as a dotted line. The parent function is 2 to the x. That's an exponential growing function. And I know that the exponential growing function crosses at 1. So this is my parent function, y equals 2 to the x. But then what am I going to do to this parent function? I'm going to shift it over to the right by 4 units. So how does that look like? It looks like something that's moved over, right, to the right. So I'm gonna, I guess maybe more using the arrows might be helpful to indicate what's going on. So the blues here, I'm shifting it over by 4 units. So this is y equals 2 to the x minus 4. And now that I have this blue curve, what am I doing to the blue curve? I am shifting it up by 1. So what is that going to look like? And if I shift it up by 1, what happens to my, so one thing you always want to make sure you have as like a boundary is your horizontal asymptote. So if my horizontal asymptote is the x-axis the whole time, when I shifted it over to the right, it's still the same, right? But the moment I shift it upward, the horizontal asymptote also is shifted up. So my horizontal asymptote is no longer at 0, but at y equals 1, because I shifted it up by 1. And so I moved the blue curve up 1 unit as well. So I got something that looks like this. Yeah, drawing this is not that easy. I got something like this. So this is my final function, y equals 2 to the x minus 4 plus 1. And again, I'm going to go through the characteristics of this function. The y values, the x-axis. So what are the characteristics? Of h of x? So the first thing is my domain. My domain always will be all real numbers. What's my range of the final function? Anybody have the range? So Tiffany, make sure you look at the green one, right? It's the green one. So it looks like the green curve is above the 1, right? It's not below it. So the interval should be changed. Yes, it should be 1 to infinity, excluding 1, right? And then the horizontal asymptote is y equals 1, because I shifted it up by 1. Um, what's the y-intercept? So this is going to be an interesting one. What is the y-intercept? How do you figure out the y-intercept? X equals 0. That's right. So I want to say x equals 0, but I'm plugging into what function? H. So what's h of 0? H of 0 is 2 to the 0 minus 4 plus 1. This is 2 to the negative 4 plus 1. What's 2 to the negative 4? It's 1 over 16, right? Plus 1. And 1 over 16 is 0.0625. So when you add it, this becomes 1.0625. So my y-intercept is going to be what? 0, comma 1.0625. So very good. The y-intercept, remember, is always when x equals 0. You plug in 0 into your function to get the y value, and then you have the coordinates of my y-intercept. So then the y-intercept here, just to make this sure here, at the end of the day, this was 1.0625 y-intercept. And then once I have that, I can talk about the end behavior. So you have to help me fill in the blanks. As x goes to infinity, y does what? As x goes to negative infinity, y does what? So as you move to infinity, as my x values go towards infinity, what does my y value approach? According to the graph, the curve, if I move to the right, my everything goes up, right? So it goes to infinity. That's right. And then when I move to the left, what are the y values approach when I move to the left? It approaches 1. Perfect. So there we go. We have everything. Very good. We have all the information we need for our transformed exponential function graph. Any questions about this? Any concerns, comments? Is this starting to make more sense? Like the whole transformations idea, how transformations are applied. So if you get to see that, if you get to see that connection between parent functions and how transformations are applied, then a lot of these problems here, like when you're able to see a function, you're able to determine, oh, I know exactly what it looks like. Or you can say, I have an idea of what it looks like. If I just gave you this function without talking about parent functions or transformations, you look at me and be like, I don't know what this is. But because I gave you the foundation with the transformations in general, and then I'm talking about, okay, these are the parent functions of exponential functions, you see how you're able to now, based upon the parent function and transformation, you're able to now come up with the new sketch of the curve. And based upon that, you're able to give me all the information that I need about this function. And that's what we're trying to build, that kind of skill set. Okay, good. I think this is pretty good. Okay, good. So we're graphing. I think it's pretty good treatment of the graphing. Uh, Now just continuing with this whole graphing thing, I'm going to give you now graphs of exponential functions, and I want you to find the formula for that graph. So now it's the opposite. Normally I give you the function, find a curve, find sketch. I'm now going to give you a curve and you have to find the exponential function. So then how do we do that? So finding equation of the function, finding the function given the graph, finding the exponential function given the graph. So an example of that is the following. If I have a graph, and it looks something like this. And this is 1. And I got these coordinates here, 2, 9. So I'm going to give you a coordinate. I'm going to give you one coordinate, and I already know this is the y-intercept at 1. So what do I know from the original exponential form? What's the exponential function form? The exponential functions look like this. F of x equals a times b to the x. That's what they look like, right? Now, what is my y-intercept? Immediately, I realize that this is my y-intercept. 0, 1. So then what does the y-intercept help me find? If I know that if I plug in 0, what happens? I get a to the b to the 0th power. That gives me 1, doesn't it? When I plug in 0, it should give me back 1. So b to the 0th power is 1. So this becomes 1. So I get a equals 1. So do you see that? My a value is 1. And you can start to say that now that the a value represents the y coordinate. Well, you know what? Yeah. For these problems, it's okay. Let's just maybe say that for some other time. But for this problem, to find a y-intercept, just plug in 0 and you find what the a value will be. So a equals 1 here. Now the problem becomes, how do you find that b value? How do you find what the b value would be? Well, that's when you use the other point, 2, 9. What does the other point tell me? It tells me the following. So use point 2, 9 to find the b value. So if I plug in 2, and my function again, my a value is 1, so I don't need to write a anymore. I just write it as 1, and 1 times anything is itself. So this is going to be b to the 2nd power, right? This equals what? 9. So remember, this thing escapes a lot of students for some reason. But when they give you a point, they're really telling you if the input is 2, the output of that corresponding input is 9. So if I input my function 2 into my function, then the result has to be 9. And this is that intermediate step that's very important. Well, the function I know has this form, a times b to the x. A is 1 already. I know that. I'm trying to find what b is. So when I plug in 2 into my function here, I get b squared equals 9. And then how do I get b though? What is the b value? The b value is 3 because when I take the square root, right? When I take the square root of b squared, take the square root of 9, I get that b value is 3. So then what is the equation of this graph? So the equation of graph above is y equals, or f of x equals 3 to the x. Done. Okay? That's how we find it. We plug in 0 to find the a value, and then we plug in the x value of my other point to find the b value. And that's all it is for this. Okay? So what if I have something like this? The a value represents the x being squared. No, the a value here represents if you want to say the a value here represents the y coordinate of my y-intercept. And x is not, a is not being squared, b is being squared. Yeah, the base is being squared, right? I'm plugging in 2. Remember, exponential functions occur as we noted in the very beginning. The note is that the exponential function is different from other functions that we've talked about because now the variable is in the exponent place, is an exponent. Whereas most of the time, the x values that we've dealt with are in the base. Now we're changing it. Now the number is a base and the variable is an exponent. Because that's the case, they're called exponential functions. Okay, so what if I get something like this? So I have a point here, and this point here is 1 comma 1/5. And 2, 2. Yeah, and then let's make this here. Let's make this a 2 instead. So my y-intercept, this is a point that I got. Okay, this is a point, and this is my y-intercept. So my y-intercept is 0 comma 2. And what am I trying to look for? I'm trying to look for the function or the equation of the function of the graph. Equation of graph. So I know that my graph is exponential and it has this form, a to the bx, right? So to find a value, use y-intercept. So what is the y-intercept? Remember, the y-intercept is when x equals 0. So when I plug in 0, a times b to the 0th power, I should get what out? I should get 2 out, right? And if b to the 0 is 1, then what does a equal? A equals 2. So now I know my a value equals 2. Okay, so since I know my a value equals 2, I know that this is going to be equal to 2 times b to the x. That's my function so far. I have to find b. So this is the first part of the problem. And the second part is find b value by using the point. 1 comma a fifth. So what does that mean? Y equals 2 times b to the first power. And this has to give me 1/5. So what does the b value equal? What does my b value equal if 2b equals a fifth? Then to find b, I need to do what? And get it by itself. To get it by itself. And what do I get for b? Anybody? How do you get b? 2b equals a fifth, so b equals 0.1. That's right. So when you divide this by 2, guys, you can also use fractions. Don't be afraid of fractions. 2b equals a fifth. If I divide this by 2, I get that b is 1/5 divided by 2, which is the same thing as saying 1/5 multiplied by a half. Keep, change, flip, and I get what? B is 1/10, which is the same thing as saying 0.1. So I got my a value being 2 and my b value being 1/10. So then what is the final answer? What is the function of graph? What is my function? I should write this as function. What is the function of the graph? My function is what? Y equals two, my a value is 2. My b value is 1/10 to the x. Now I want to note something, okay? I want to note something. Note that let me just write this. Let me use another A. No, let me use another letter. T, okay? T to the negative x is also written as 1/t to the x. Remember this? And what I'm saying is there's 2 ways to write 1/10 to the x. I can also write this as 2 times 10 to the negative x. And if you don't believe me, you can just take this 10 to the negative x and make the exponent positive. So you can write this as 10 to the negative x, right? 10 to the negative x is also written as 1/10 to the positive x, correct? But I can also rewrite this as 1/10 to the x and raised to the x power. Why can I do that? Because 1 to any x power is always 1. And because now these two bases have the same exponent, I can rewrite this as having one single fraction here raised to that power. So really, I'm just trying to show you that these two things are the same. They're equal. Okay? So I can rewrite the function in 2 ways. I can rewrite this saying as a fraction, 1/10 to the x, or I can write this as 10 to the negative x. Okay? So any questions about this? Any questions about exponential functions, the graphs of exponential functions? No? No questions? Okay. So now the question becomes, okay, great. We've talked about exponential functions. We talked about the graphs, the domain range, and behavior, transformations of different kinds of exponential functions. Great. But why do we even talk about exponential functions? Why is it just for math class? Is it just to learn some more math? Well, I would venture to say that exponential functions are probably the most applicable function to your life. Um, I would say, I could be wrong, but it's just that there's so many actual things that occur in our world that have an exponential trend. So for one of them, population growth is exponential for the most part. Um, you can test that out with species. You know, people have tested how rabbits, for example, they multiply pretty quickly, or reproduce quickly. That's one example. But of course, maybe you're not into rabbits or into animals. But I know there's something that a lot of people are very interested in, and that's money, right? We all, when you hear money, your ears start to just like, you're like, wait, what about money? So exponential functions are essential. Okay, they're essential. If you guys are interested in mathematical finance, um, of any sort, exponential functions are like the first thing you learn. In particular, we talk about what's called compound interest. You may have heard this before. I'm pretty sure you have. So compound interest. What is compound interest? So first I'm going to give you the formula. And you probably have seen this formula before. Now, what does the p-value represent? Does anybody has anyone seen this before? So the p represents what's called the principal amount. This is also known as the initial investment. R is the annual rate. It's the annual rate of interest, or I should say annual interest rate. And we normally write this as a decimal. If the rate is converted from percentage to decimal. So convert from percent to decimal. So we're always going to express our rate as a decimal for our formula. N represents the number of times that interest is compounded, quote unquote, per year. So how many times is our interest compounded? And finally, T represents the length of investment period. And we're missing one actually, A. A represents what's called the accumulated value. So all of these little letters here are represented by real world meaning. So this gets really important when you talk about investments that you might be interested in making, right? If you have a certain amount of capital and you want to double it, you want to triple it, you want to make it grow for a certain amount of time, what's going to be very interest to you is, without another pun being intended, is the annual interest rate. You want to know how high or low the interest rate is for your account, for your bank savings account, for your, I don't know, So many different accounts out there that help you make money. And then you also want to see if they do have this kind of compound interest per year. If they do it once a year, if they do it twice a year, 3 times a year, 4 times a year, monthly. So all these things matter. And how long do you want your investing period to be? So these things occur in real life. And of course, this is again, this is like a basic foundational knowledge of mathematical finance. And of course, things get very complicated as you get more advanced. But like I said, this is the beginning. And this is a exponential function. This is an exponential function. Why is it exponential function? Because this is a function of time. And time here is my exponent. So this is an application of exponential functions. Okay, so let me give you an example of one. So suppose you invest $1,000 at an interest rate, at an annual interest rate of 12%. Find the amount, find the amount, um, find the amount after 3 years if interest is compounded monthly. So the wording here is going to matter a lot, right? They might use different words for compounding. They might use compounding monthly, compounded weekly, compounded quarterly, semi-annually. All these words mean something. So let me just make that note here. So we have different words for compounding. So if you're compounding annually, obviously, right? Annually is just one. If you do it semi-annually, that's two. If you're doing quarterly, that's four. If you do it monthly, that's going to be 12. If you do that weekly, that's 52. And if you do it daily, it's 365. So what I'm talking about is the end value. The end value is going to change. So these words matter to for the value of the end. Okay, so n is 1, this is 2, this is 4, this is 12, this is 52, this is 365. So that's what the end value will be. So these words indicate the end value. So in this case, my interest is compounded monthly. So immediately I should say n equals 12. So then what is, by compound interest, the formula, what do I have? I got that the A value is this, the P value, so the A value is missing, the P value is 1,000, the R value, what's the R value? If the annual interest rate is 12%, what's the R value going to be? Remember, we always want to convert percentage to decimal, and that's right. To make the percentage into a decimal, you move the decimal point to the left 2 units. So you get 0.12. The n value is 12, and the t value is 3. So all I have to do now is plug in everything into the formula. So I got A is equal to 1,000 over 1 plus 0.12 over 12 raised to the 12 times 3. I plugged in everything, right? I plugged in everything into my formula. And so let me just write this, write the base out. So I do, if I do 0.12 divided by 12, and then I add this to 1, oops, add this to 1, I get 0.01. So the base here is 1,000 times 1.01. 12 times 3 is 36. So when I write this out and I put this in my calculator, 1,000 times 1.01, and that's raised to the 36th power, I get 1430.70. So I get 1430 points, 0.7687. 7687 dot dot dot. But of course, I'm talking about money here, right? So we're going to round it to the nearest cent. So if I round it to the nearest cent, I make $1,430.77. So that's how much money I make over 3 years. In 3 years, that $1,000, if it's compounded at an annual interest rate of 12% monthly over 3 years, I make $430.77. That's how much interest has accrued to my original amount. Does that make sense, guys? The annual interest, compound interest. So it's really based upon the formula. So if you know the formula and you know what all these values here represent, then it's really just a plug-in, put in your calculator, and you get the final answer, the accumulated value. Okay? Okay. So that makes sense, right? Now, okay, so don't Sydney, don't get confused here. I know it just happened to be that the annual interest rate was 12% and the compound interest is also 12. What we converted is not the end. We never convert the end. The end is always a whole number. We just convert the percentage. It just so happened that the percentage was 12%. So if this was like 5%, then the R would be 0.05, and then you would have 0.05 here, and you still have 12. So that's why, yeah, don't let that confuse you here. Even though they're both 12s, it's two different things. One is the annual interest rate, and the other one is the number of times that's compounded per interest. Okay. Yeah, maybe I should have used another number so that there's no confusion of that. But like I said, if you identify all the correct variables here that I have, if you identify them correctly, then plug in the formula shouldn't be too hard. And hopefully with this next example, you'll see that. So what I want to do in this next example is very particular. So I want to figure out what's the best I can do in terms of compound interest. So I'm going to start out by saying I'm going to have a principal amount of $1. Okay. Let's just suppose you have $1. That's all you got. And let's suppose that there's some bank. Okay. Of course, this bank will never exist. But let's suppose that they give you an interest rate of 100%. Isn't that probably the best you can do? Like, just think about not the real world for now. Just think about the best that can actually happen. An ideal bank would be, hey, if I put in $1, I get back another one. So I make double what I made, right? So then suppose that my interest rate here is 1, which means, I mean, the decimal is 1, which means that I have 100% interest. So suppose there is a bank that offers 100%, that offers an annual interest rate of 100%. So immediately R equals 0, right? Suppose that there is a bank, and you start out with, you invest $1 in this bank for 1 year. So the t value is also 1. And then the question is, find out how much the account has if interest is compounded. And I'm going to do it for almost every single one. I'm going to do it when n equals, when the interest is compounded, I'm going to do it annually. That means that my n value is 1. I'm going to do it semi-annually. My n value is 2. So on and so forth. What happens if I do this semi-annually? Then we have quarterly. My n value is 4. And then I'm going to do this monthly. My n value is 12. And then I'm going to do this weekly. My n value is 52. And then I'm going to do this daily. So you might be like, wait, you're killing me here. You want to do all of this? So I just want you to get the idea of what's going on. So I'm going to be applying this formula the whole time. P1 plus R over N to the NT. It's just that a lot of these are going to be ones everywhere, right? We're going to have, for example, if this is done annually, 1, N equals 1, R equals 1, T equals 1. So what do I get? I get 1 plus 1 over 1, 1 times 1. What does this become? 1 times 2 to the 1. I get what? $2. Doesn't that make sense? If the interest is compounded once a year, so I'm just doubling it. I'm starting with $1. After a year, the bank is going to give me 100% back. So I got $2. Of course, that doesn't happen in real life, right? You put in $1, and the interest rate is probably, I don't even think that's a cent of an interest rate. I think it's way less than that. So usually bank account interests are what, like, I don't know, is it like less than a 1%? I don't even remember. But does everybody see that? If you have $1 in this bank account, you'll produce $2, right? After a year. Now, what if instead of the interest rate being compounded once a year, what if it's compounded twice a year? What would the difference be? Would I make more money? Well, most likely, right? Now this will be 1 over 2 now because n is 2. You see that? You see how it changes? Now this is 2 times 1. This is 1 times what? 1 plus a half is what? 1.5. And if I square 1.5, what do I get? What happens with my dollar if my annual interest rate is compounded twice a year instead of once a year? What's going to be the difference? So what is 1.5 squared? 2.25. Oh man, I made 25 cents extra. So I made 25 more cents. So what do you think is gonna happen if I do this instead of semi-annually? If I do this quarterly, what's the new amount that I make? All I'm doing is changing the end value. That's all I'm doing. Everything else is ones, right? So I get 1 plus a fourth is what? 1.25. If I raise that to the fourth power, what do I get now? Does anybody know? And round it to the nearest decimal. I mean, round it to the nearest cent. So 1.25, if I raise it to the fourth power, becomes what? All I have to do is raise 1.25 to the fourth power. That's right. Thank you, Felipe. 2.44, right? So look what's happening. Something expected, right? The amount that we get after it's compounded more times per year, we get more money. So it's obvious that we want this to continue, right? So if I do this now monthly, what would my new account balance be? What would this be now? 1 plus 112 to the 12. How much would that be? Did anybody get it? 2.61? Thank you. Yes, Sydney. 2.61. So what do you guys think? Do you guys think that this is just gonna go up forever? What happens if I do it weekly? What is this gonna be? 1 plus 1 over 52 to the 52 power. Did anybody get this one? 2.69. Wait a minute. Wait a minute. Do you start to see something? What's happening? Do you see how these numbers, the increase of each number as I increase the number of times, it does get bigger, right? But it's getting bigger at a smaller rate. Yes, exactly, Sydney. So what is that? What is that trying to show us? That this fictitious world in which it's 100% annual interest rate, which is never going to happen probably in our life, uh, and the number of times that we're compounding it, there is a limit. It's approaching some number that doesn't. So our goal here is to figure out what is that number that we're approaching, if there is such a number. We could be wrong. It could be increasing every single time. Ah, here we go. Here we go. So if I do this every day, if my interest rate of 100% is compounded every day, Felipe just found that this number is $2.71. Hmm. So you see how these, the increase, right? This was 25 cents increase, but then this was what? This was 19 cents, right? And then this becomes what? Is that 17? 17, and then this becomes what? 8 cents, and this becomes what? 2 cents more? And think about it. This is done 52 times a year. And then I just ballooned this to 365 times a year. And the best I could do was 2 more cents. So then the question is, can I do better? What do you think is better than doing it every day? Can we do something more than every day? Every hour. Oh, wow. Okay. That sounds good. So what do we have to do that? Every day is 24 hours. Multiply 365 by 24, which is what? 365 times 24 is 8,760 hours, right? So then you would say, hey, you know what? Let's do it better. What's better than this? Well, if I do this every hour, then n is what? 8,760. But then do you guys see what the problem with that is? Well, not the problem. Oh, what happens when I do this every hour? I'm going to do this every hour, guys. What's my new result? Can anybody figure that out? What is my new result? I get 2.7, 2.72. Do you guys see the increase? I did this yeah, I did this from 365 times. I did this now to 8,760 times. I'm compounding the interest. And the best I could do was 1 extra cent. Can we do better than an hour? So the question is, okay, let's do every minute. Sure. Then what does that mean? Multiply 8,760 by what? By 60? Because we have 8,760 hours in a year. So every hour has 60 minutes. Multiply that by 60. Do you guys start to see the trend? Okay, this will be the last one that we do, okay? 8,760 times 3 times 60. That's 52, right? 52, no, 525,600 minutes in 1 year. So if I do this in a per minute, n is what? 525,600. So guys, what do you get? You still get 572. What? I thought this would go on forever. Sorry. Sorry, Charlie. This is the best. The best you can do, the best you can do is if you live in a world where your bank account would return 100% of your money and you had $1 after 1 year, the most you can make is $2.72, and that's it. Now, Chen, you touched upon something very interesting. Compound continuously. And that's where I'm trying to get at with this. The question is, can we do better than a minute? Yeah, we can do every millisecond. Oh, we can do every second. And then we're like, okay, seconds are not good enough. What do we do every millisecond? But millisecond, can we do finer? Can we do every nanosecond? And it gets kind of like, okay, how much can we cut time in? Then it becomes, you know what? Let's just make this every instant in time. Now, how in the world do we calculate an instant in time? Now I'll start to think about that. How do you capture an instant of time? Have you ever thought about that? There's something about time that's very There's something about time that is very particular. It's quote unquote continuous. It's opposite of being discrete. Discrete are things that you can tangibly count. You can say, oh, that's one, that's two, that's three. That's discrete. You can count the number of cars. That's discrete. But when there's continuous, it's something that you can't just take a piece of it. As much as we want, we can't take a piece of time out. We're living in this world where time just flows. You understand? So the idea here, when we talk about compound continuously, means that at every waking moment, interest is being compounded at every instant. And the only way we can actually think about this is by saying that as n approaches infinity. Do you see now how this stuff comes from the n behavior? These terminology comes back again. This little arrow. As n approaches infinity. What am I interested in? I'm interested in this, right? I'm interested in 1 plus 1 over n to the n. At the end of the day, that's what I'm interested in. As n approaches infinity, what in the world does this approach? You've been doing this the whole time. You see, the n values get bigger and bigger and bigger. And now what happens when n goes to infinity? Meaning that I'm compounding this every waking moment of my life. You know what this approach is, guys? It's not 2.72. We're rounding it every time. You know what this approach is? Anybody have a wild guess? Maybe someone has seen this before. But guess what this approach is, guys? E. That's what this approach is. You're like, what? It's a letter? Yeah. E is a constant. It is known as Euler's constant. Euler comes from the mathematician Leonard Euler. And it's not Euler, it's Euler. He's German. And yes, if you put this in your calculator, E is has an infinite decimal expansion. And E is 2.71828 wait, 18281 dot 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 dot. This goes on forever. This is an irrational number. This is actually called a transcendental number. This is another craziness. Transcendental number. This E value is comparable to pi. So just the same way as pi is irrational, it's also transcendental. And it's embedded in circular shapes. E is even more impressive. Why is it more impressive? Because E that does not only appear in this kind of world with banking of 100% interest rate. It's also in nature. The way things grow and decay has this embedded in it. So that's why this is very impressive constant that appears in our world. Okay, so that's what I wanted to get at today. I think this is really cool. Like, there's actual limits to things, and these limits have a very specific number, and these numbers appear in our life. Cool?